Good. Let me start with a very brief recap, reminding you of a few of the things that we found out on the way. So we've been concerned a lot with representing quantum many-body states, and one of the new additions in the lecture yesterday was that we had this diagrammatic notation, and the quantum many-body wave function is described by the amplitudes psi with indices I1 through IL. And what we are concerned with are now one-dimensional systems. So we just align our sites on the chain, and we then this L tensor in terms of a blob with Lx sticking out. And then we found these rank L or order L tensors can actually be well approximated by the following structure of a matrix product state, like of this form, where now what we have done is that we decompose our order L tensor into a product of many order 3 tensors. And by this, what we did is we reduced the number of parameters significantly, because here, assuming that we have a local Hilbert space dimension D, here we've got to store D to the power of L complex numbers for describing the state. And now we just reduced it to something which is L times chi squared, where chi is now the dimension of these tensors, often called as the virtual dimension or virtual bond dimension, times D being the physical dimension. So the upshot is that if we just do this, we actually reduce the number of something that's growing exponentially to the system size to something that grows only linear with system size. And that, of course, can't work in general, but it does work if we have an area law. Good. So, and then we went a bit further, and we realized that there's a gauge degree of freedom, like, because basically whenever we can just have like some transformation x and x minus 1, if we just put these on, then and so on. So then we see that this gauge transformation doesn't change the physical amplitudes in the many-body wave function, but to a different matrix product state. So the tensor product state representation change. So and then we can use it to our kind of convenience. And what we then did is we just represented our tensor network state in the form that we have gamma, lambda, gamma, lambda, gamma, lambda, gamma. And now these lambda matrices are diagonal matrices that contain the Schmidt values, and these gamma tensors are now tensors relating the local space and the Schmidt states. And then basically, if we have this form, we can just basically get a Schmidt decomposition for free. So we just like say we fix this index here to some alpha, and we just multiply all these tensors together, then we exactly get our Schmidt states on like say for subsystem A, which is like on the left. And if we just contract everything here for a given index alpha here, then we get here the Schmidt states psi alpha B. Right, and here are now our Schmidt values lambda alpha. Right. Good. So this is what we call the canonical form. And we then, and this is what we closed with on the last lectures, we said that, well, if we now have an MPS given in this canonical form, then we introduced an algorithm that allows us to perform time evolution efficiently. In particular, what we assumed is that we have a Hamiltonian that is of the form where we have the sum over all lattice sites and then hi I plus 1. And then we just found that, well, we just have our MPS, say, at a in this form here again at some time t. And if we now do the time evolution, we can now trotterize the time evolution with small time steps, and then by this perform one time evolution step. So basically what we do here, we just approximate the time evolution by some small time step delta t. And the way that we, right, so now we just start from an MPS, we're just applying or multiplying these things using exactly the rules that we got to know earlier. But then this doesn't have the form of an MPS anymore. What we then need is an algorithm that gets us back to an MPS, which just compresses this back. And then this is where we introduce the TEBD algorithm. That does then, and the way that we did it, we just kind of take some parts. So for example, we just take this bond here, compression of the bond, just using the SVD singular value on this object, and then this is a representation of the many-body wave function with respect to a mixed basis, basically the orthogonal Schmidt states on the left, orthogonal Schmidt states on the right, and local states here. So very good handle for doing the compression. Good. So and then I demonstrated that this actually works, but there's a few things, and I just mentioned it in words. I want to quickly maybe also write it down. If we are doing this, there are now multiple approximations built in. So one is that we have what's called the truncation error. The truncation error. And this is what we get when we apply the time evolution operator on a given bond. What we effectively find is the bond dimension or the matrix dimension on this given bond is actually larger, and then we have to reduce it, demonstrated yesterday. But then we are just throwing away some Schmidt weight, and how much away depends on how much the entanglement has gone, right? So basically we have this step where we have a dimension d times chi, and we reduce it to chi, and then we are throwing something away. And this can have quite some effect if the entanglement of the wave function is growing very quickly. I showed this yesterday for the last example where we did this quench experiment, where we started from a simple product state, which we can represent very easily, but then as time went by, the entanglement was growing linearly, and that meant that the bond dimension is increasing very fast. And then this is that we should monitor. Right? So basically, if you are now writing a code, performing a quench or doing this, at each step, you should monitor how much weight was thrown away, what is the truncation error, and then you know that, well, if the truncation error is maybe larger than 10 to the 8 or something like this, you just know that this is the time to stop. And then you just either need to get a bigger computer that can store larger matrices or just think about some other ideas. So this is really the thing that one has to be really careful about. But then there's also another error, and this is a error. So we are and doing it in the way that this is implemented here is just a first order trotter decomposition. So we have the trotter error, which is of order dt. So basically we have the trotter error, and the trotter error is of order dt. Or the way that I introduce the algorithm here, it's not too hard to go to a higher order of a trotter decomposition to do it second or fourth or whatever order. So the order of the trotter decomposition, or you make you just can make this dt smaller. But in all practical purposes, this is usually not the limiting part, right? So you just make sure that O of dt, or like some order of dt to the power of n, if you have a higher order, is small enough, then this is usually good. Then there's the last error or problem that I want to mention, and this is because the algorithm, the way that I introduced it, is heavily relying on this canonical form, and the canonical form is not violating we are performing a unitary time evolution, which is the case for real-time evolution. And then everything is working exactly the way that I was promising it. If we do imaginary time evolution, the operation is not unitary. So if we apply a gate, this is actually destroying the canonical form. That is a problem for successive truncations that we are doing, as I mentioned, because maybe I was even talking about it too long yesterday, but for the truncation to be optimal, it's really important that we keep this orthogonality, right? So that the Schmidt states are actually orthogonal. If we do imaginary time evolution, we do violate this, but the thing is that we're just doing each time fairly small. The operation is almost unitary, and one trick, as I showed yesterday, to overcome this problem is to start with a fairly large time step, to just move quickly, basically, and then as you want to go closer to the ground state, you will then reduce the time step, and by this also get basically closer to the canonical form, right? So the canonical form is violated for imaginary time evolution. So basically what we want is like make delta t really small in order to cure this. Good. So this roughly concludes what I wanted to tell about the TBD method. But let me now, also for practical purposes, advertise one thing. Is that because in the last lecture I showed how to write this in a few lines using NumPy. And I think this is really good to understand it and to see the limitation and strength of the method. But for practical calculations, it's often better to use one of the existing libraries. And there are several libraries on the market, and there's the iTensor method, and one method that we are, or like one package that we are developing in our group. And this is actually a package that grew out of a collaboration with Mike Zaletel and Roger Mong when I was postdoc at Berkeley a long time ago. But this is now mostly pushed by Johannes Hauschild, who is taking care of the code base and most of the code development at the moment. And then using these packages, it's like many of the kind of core methods and many models are included. So if I, for example, want to do the time evolution or the imaginary time evolution that we looked at yesterday, I want to do it in 10Pi, I can just write this rather compact code. So I can, from this tensor network library, I have some package for matrix product states. I have various methods, various models, including the transverse field Ising chain, and a large set of algorithms. For example, the TBD algorithm that we just introduced. And now, well, we can just define a model by just passing the parameters. We can then define an MPS, given here, for example, that we just initiated with a ferromagnetic state on 16 sites. We can define the parameters for TBD. And as I said, like the way that I wrote down the algorithm, it's just the first order algorithm, but here you can, for example, just tell it what order to do, and by this getting then more accurate data. If you increase the order, you can define the error that's accepted, and so on and so forth. And then you define with all this the engine. You can run the engine, and then you get the results, right? So if you're having using these packages, the code is actually then fairly easy to write. Yes.
Typically propagate as you increase the number of time steps. How much does it tend to increase?
I think it's difficult to. I mean, you can just write down like some sort of bound by basically summing up all the truncation errors, but it's not a very accurate one. So I think that as a rule of thumb, the moment that you start to truncate, you should basically stop. Then there's no way to really trust the data afterwards anymore, right? Because as I'd shown yesterday in this example, when you just do the time evolution and you truncate, then, for example, even like energy conservation is no longer obeyed, and things. Yeah. And in practice, at least, this is we and the other groups are doing. So you just do simulations for increasing bond dimension, and then one is getting maybe plots like this. So you just find something like this, and now you see that, well, if you just increase the bond dimension, it looks like this, and then you just increase it further, it looks like, and then you would say that, well, there's a certain regime where you do trust the data, and yeah. Good. Okay, and now it's right. So this TBD method has certain limitations. So one limitation being that at least in the direct implementation, we are limited to Hamiltonians that act only between neighboring sites, and also using imaginary time evolution for finding the ground states is not really the fastest way to do it. And then there is now a much more powerful method, and this is the density matrix renormalization group method that I want to now introduce. And there's, I think, also historically something quite interesting, because maybe it was Stephen White who came up with the density matrix renormalization group method, and this is because he was thinking about kind of numerical RG, where the truncation is done in terms of energies. And then it turned out that that method didn't work for certain problems. And let me maybe put this here as sort of an interesting remark or story. So one, like, let's say that you know how to do small systems, and then you say that, well, let me first find the ground state in a small box, and now I take the ground state and the lowest excited states I'm just now taking for this box, and now I'm just keeping the very low energy excitation, and now I'm, say, doubling the size of the box, and I'm now forming a tensor product state of the low energy states for each for this box, right? So now I just take then the tensor product states of the low energy states. That seems not to be a very stupid idea for a increasingly kind of single out an effective low space to describe my problem. But there's a very simple problem where this is going horribly wrong. And the simple problem where this is going wrong is by just solving the problem of just a single particle in a box. If I put a single particle in a box, well, the ground state is going to be a wave function that looks something like this. Then I get some excited state, which is like looking like this, and so on. But if I now play exactly this trick, first find all the low energy states that are good for my single box, and just putting them together, then this is actually a very bad basis for describing the states. So basically the states that I have is something like this, but what I want to describe is something like this. So this is one of the problems that he was confronted with at that time, that that this simple, or like this kind of otherwise kind of very successful method is failing for some very simple problems. And then he thought that, well, maybe there's a smarter way to do the truncation. And the way that he just truncated is then, well, he just did the truncation using the reduced density matrix, exactly the object that we've been talking about earlier on. So this was sometime in the early 90s, where he just basically came up with then a different way to grow the system, a better way to truncate states, and then had this RG view of it. That's why also it's the name of a density matrix renormalization group method. Do you have a question?
Yeah, I'm just wondering, can you elaborate a little bit how reduced density matrix solves this issue? It seems like every time it seems like it's pretty intrinsic. So how do you?
Right. So the way I visualize how this is fixed is now the following. So so this is just the standard RG picture. Oh, let me introduce very similar language what Steve White did, or like basically his mindset at this, how I would interpret it. So basically now the idea is you just find the ground state for your small box. And the ground state for the small box is now looking something like this. And now what he did, or like the original algorithm, is now the following: that, well, let me now do a cut here, the same way as we did before. Let's do an here, or look as like, let me just use SV, because on Monday I told that the eigenstates of the reduced density matrix are actually equal to the to the Schmidt states, right? So let us now do this cut here, and we do either doing a Schmidt decomposition, or we are diagonalizing the reduced density matrix for, say, for the left half, and now I'm taking these states. So now I take those Schmidt states, like now taking these Schmidt states that have a very large weight, or I take the dominant eigenvalues of the eigenstates corresponding to the dominant eigenvalues of the reduced density matrix to describe now the left part. And now I add some extra sites to the middle. And then I'm taking these states here also, right? So now the states that I'm getting here are exactly of this type, basically. And here I'm getting these types, and now I can add these in the middle. And now I'm just solving my problem for this one. And now again, I'm doing a cut here. And this is basically how this problem is like visually overcome, right? Because here the problem is that if I take the low energy state for this box, it's really useless for describing the ground state. But in the way that Stephen White thought about this here is you can just now grow the system, and you just keep now the dominant states or dominant eigenstates of the reduced density matrix, and then you get something.
Why the dominant one, the shape that you drew? What does that mean? How do I see that the dominant one is the little?
Because if we have a wave function where the particle would have, like, if we were to have let me just, because if you just do this in momentum space, let me just think about for a second. Right. I mean, if we just think of this being a momentum, like let's say that we just take a single particle on a lattice, a single particle hopping problem. In this case, if I'm doing the Schmidt decomposition, I'm only getting two non-zero eigenstates because either the particle is on the left or the particle is on the right, but there are many more states which just have zero, right? So basically, then I'm getting exactly the contribution that make the ground state on the left half. So I'm getting the full wave function on the left half. So for the single particle problem, there would actually be zero approximation. It would be perfectly exact. But so basically, if you just do the Schmidt decomposition, let's say that we have now a state which is just a superposition with whatever kind of amplitude, I don't know, psi n, where say I have my particle sitting on the and now I can just write it always as something like some wave function where maybe it's zero, so there's no particle on the right, and you've got a wave function on the left with some amplitude x plus some amplitude y times nothing on the left and just the particle on the right. Right? So, and then this is exactly making this wave. Right.
Thank you.
Good. So this is basically, this was a story in the 90s. Yes? No. I mean, this is, I don't Or at least I don't see how this is the decisive part here. Because if you, I mean, you can even have.
What sense of the gap was?
Well, that's like the low energy and the lock boundary.
That you get extended wave function that I think is the problem. It's not. I mean, if you just, I think that if you just tune the Hamiltonian, you can probably also. I mean, I can't do this in my head now, but I'm pretty sure that we can cook up a model which is gapped, and the this RG model would also fail. I mean, that is not the most important part.
Also, it seems like that like it's a different problem also.
No, but you can just write this on. You just solve a free particle hopping problem on a lattice. But you could say that, well, take a tight binding model of a particle hopping on a lattice. That would be the same story. Well, but the Hilbert space is, I mean, the Hilbert space in which this problem lives is then the problem side. You just look at the sector where there's just a single particle. I mean, it still lives in a Hilbert space which has this product state basis. So as I'm shown here, like for this kind of problem. Yes.
So for that language,
Uh-huh.
they actually formulated Hamiltonian with longer range.
Yeah, there's no problem. You could just say that, well, let's get you having your Hamiltonian on this box with longer range interaction, and then you just project the Hamiltonian into so that.
Keep going this.
Mhm.
Some interaction with that and right. Keep occur and disappear.
Mm-hmm. Right. Oh no, this is actually a good point. I think this is where this simple picture actually probably stops working. But there is actually another step to this DMRG, which basically this is the first step of DMRG, which I'm explaining here. But then there's another one where you then keep sweeping left and right.
Just keep going.
If you know, I think if you just keep, yeah, if you just keep going, I think one can come up with cases where this can go wrong. Exactly. So this is basically what I'm doing right now is I want to give a bit of a historic overview and then give a formulation in terms of matrix product states in a moment. Good. So right. So basically, my main point I just wanted to make is that the original motivation for Stephen White to come up with this method is the one that I just gave. Thus, it's the name of a density matrix renormalization group method. But what I want to do now is I want to just reformulate it, and it's exactly the same method. Nothing changes about the method. It's just a different way to think about it, and this is completely equivalent. And this is now a variational method, and it's basically saying that, well, I have a Hamiltonian, right? So basically, the story I say that I have my Hamiltonian, and now I'm just basically writing some sort of an energy functional where I say that I have psi h psi divided by psi. These wave function psi is given in terms of a matrix product state, like an MPS of dimension chi. Right. So now I have my family of wave functions contain where did I write it? Like that many parameters. And now I can ask that, well, for my Hamiltonian, what in this manifold, what is now the best approximation of the ground state? Right. So if I want to just minimize this expression, and this is exactly what DMRG is. And now I want to, using matrix product states, I want to introduce this algorithm.
Can you say,
Yeah.
the original DMRG, you were saying you grow the system.
Yes.
Side at a time. In this approach, you just take the full MPS wave function
Mhm.
and just minimize it, use it as a variational wave function.
Yes.
So there's no growing.
Right. So this is what I mentioned before, that if you're just using Stephen White's algorithm in this way, you would not something which will get probably close to the optimal solution. Best also in Steve White's algorithm, which he also introduced, is like you do this growing once and then you just iterate left and right to actually converge then to the best.
Optimization.
That's in the optimization. Yeah. And
The
that,
growing part is just creates effectively matrix product state.
yes,
Right.
it would just create the first matrix product state, but because of what's mentioned before, like maybe there are some long range parts in it. That's why you just might not necessarily get right away the best solution.
But the structure is the matrix product.
Yes,
state,
that's right.
just because of singular value decomposition.
That's right. Yeah, it's the same type of truncation that you get. And I think that once I put it into this matrix product state formalism, I think that this algorithm will be also more transparent. Because like when I just was giving the algorithm here, like at each step you have to do a rotation, you have to project the Hamiltonian into this effective basis. So that's actually a lot of bookkeeping. It's not super easy to code. But if we just now use the formalism of matrix product states that we are now all super familiar with already, it's actually much more automatic, everything. Good. So let me now, because yeah, this was really as a way to explain why it's called density matrix renormalization group, and then you just maybe you can do what's the renormalization type of view of the method. So now I want to discuss the density matrix renormalization group method. So now I want to basically interpret it as a variational method in the manifold of matrix product states. And in order to have a nice formulation of this algorithm, we need to introduce now one new concept, and this is this concept of matrix product operators. Matrix product operators. And the key idea, and now you probably will also learn more to appreciate this graphical notation. It's very intuitive. We would say that, well, like an operator O acting on our vector space using this graphical notation is of this type. It's now just a blob with a leg sticking out the bottom and the top. Like, well, these are already kind of simple operators, right? So we just only act on two sides. This would be now an operator acting on L sides on our entire vector space. And now I want to write this operator in terms of a product. Like the direct analogy of matrix product states of this form to the space of operators. Right? This is exactly analogous. Now it turns out that many operators, in particular many Hamiltonians that we would care about, we can now just directly rewrite into this form. And I want now to just show it for one specific example. And this is now again our Ising model, the Ising model that we've been interested in. So it's minus J, the sum over sigma zi plus 1 plus G times the sum over I sigma I x. And let me now, before I tell you the matrix product operators, I want to give you a sort of finite state machine that would do it. So there's like, if I want to construct this Hamiltonian, what it actually means is that I have to superimpose many terms, right? So I have negative j times sigma z, tensor dot sigma z, tensor dot identity, and then minus j sigma identity, tensor dot sigma z, tensor dot sigma z, tensor dot identity, and so on, right? So this is a very compact form of writing the Hamiltonian, but what we actually mean is now the sum of all of those terms being the tensor product of these Pauli matrices. And let's say that we are running a business and I want to just give someone the task to construct exactly this Hamiltonian. There's a very convenient form of writing the program how to construct the Hamiltonian using so-called finite state machines. And the finite state machine is that, well, we are just first in an initial state of our machine, and now certain things can happen. So we can now, for example, place an identity, but then we just go back to our initial state. So we just keep placing identities. This was the only instruction in our finite states machine. It would just create product states of infinitely many, and just keep going on producing product states of identities. But now we can also have another process where it now places, say, a sigma z operator. And if it places a sigma z operator, it goes into some intermediate state. But right after it's in the state, it then places another sigma z operator. And then it goes into what we call the final state. And then once in the final state, it's going to stay here forever. And then it's just placing again identities. Another thing that it can happen, it could place sigma x, well here, so we have here a g, and here we've got maybe a j, and then it goes right away to this. So if I write down this finite states machine, it's like a perfectly fine instruction to construct this Hamiltonian. So it's a very important point of view. But now I can write a matrix representation of this finite state machine. So I can just basically take the state. So I first have here the, this is for my initial state. And if I place an identity, I stay here. Then I have a sigma z. I have a g times sigma x. I have a negative j times sigma z. I have the identity 0, 0, 0, 0. This is now my matrix. So now this is just a rewriting of this finite state machine in terms of a matrix representation. And now you can actually convince yourself if you basically take I don't know, L equals to 3, I can now start from a state where I put myself into the initial state. I put now this product of some of these matrices, and then I'm projecting it to the final state, that this is exactly giving me the Hamiltonian. So basically, this is now exactly performing this finite state machine for applying it 3 times, and this would give me the Hamiltonian for three sites, and this amounts to just multiplying this matrix 3 times and projecting onto the initial and to the final state. If you don't trust, you can now multiply these matrices together and see that it actually gives you back all the terms that we get for this Hamiltonian that you need for however many sites you want to choose.
Kind of looks like an operator version of my machine.
Yeah, probably is also a way how to interpret it, yes. So you could just basically would say that you just put into a state and then you got that probability, and so yeah. Yes?
So initial vector is 1, 0, 0, and you end with 0, 0, 1. How do you know that?
Oh, because this is we have the final state. And this is the last, like this is the, sorry, this is the initial state and this is the final state. Yeah. I mean, time interval is not demonstrating, but maybe if you feel unhappy about this, just by hand multiply these matrices and see how you're getting them the right terms. And this now is exactly an MPO, right? So because the way that I construct this matrix, the elements here are like matrices with a physical indices. So here we have now a chi by chi matrix. Like, I don't know, let's say that here it's chi and here it's chi, and each of these elements it's a D times D matrix, and these are now dimension here. So here is dimension D, here's dimension D, here is chi, here is chi. So now if you just multiply those tensors here together, you're then getting the operator acting on your vector space. Yes?
These guys are different from one dimension.
This is it, right? So, well, this is also Bond dimension, but this is the Bond dimension of the MPO. And in fact, I could call this maybe capital D as I'm doing it also in the code. So just to not confuse it with the Bond dimension of our matrix product state. Right? Now, if we, let me go maybe, yes?
So M is the 6 by 6 matrix, right?
Well, I mean, the way that so you can either write it as a 6 by 6 matrix, or as a right. So basically, you can either. So we have an object which is of this form. So we have here dimension D, 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 and this object you can of course write as a capital D times lowercase d times capital D times lower times d matrix, or you can think of this as being an order 4 tensor.
Oh, so in this case it's being called a higher.
That's right. Yeah. Mm-hmm. Yes.
It's a product.
Oh yeah, sorry. It's a product of these matrices, and you just have a tensor. So I don't know if I just maybe do it for a very small matrix. So if I have this matrix here, sigma z 1, like this one, for example, and I use this notation here, what I mean is that I'm doing a matrix multiplication, but I get the tensor product of this. So this one here, for example, would now be a matrix where the first element here is 1 tensor dot 1 and 0 times this, so this doesn't count, and then the next like the element here would be then 1 tensor dot sigma z and so on, right? So basically the operation how I multiply the elements of my matrix would be a tensor product. Yeah. Yes. Right. So this depends now on what kind of Hamiltonian you have. So for example, so if we would only take the transverse field term, then all this one here would not occur. So then this would be just the 2 by 2 matrix. Right? So because then we just need to go from the final state to the from the initial state to the final state. But here we have to have this intermediate state x in between, which gives us now 3 states. So basically the dimension of the matrix is equal to the number of states that I need in my finite state machine. Right? So for example, if in this Hamiltonian we also want to have a sigma x term, right? So what it would mean is that then we also have a state that we have sigma z. Now we have another intermediate state, and then we go here. So now that would mean that in this case it would be a 4x4, like D would be 4. Yeah.
Is it just a range of interaction plus one?
What's it?
Is a chi just the range of interaction plus one?
If you just choose a super naive doing this, yes, but this format allows you just much more general interaction. If you think in terms of this finite state machine, for example, let's say we would also allow a transition from here back by placing an identity, or maybe like putting here some alpha times an identity. Now you see that you just get all sorts of terms where sigma z is right next to each other by just going here, going back, or you just go here, place an identity, place some alpha times identity, then go on. So basically, if you have this, you can actually have a Hamiltonian with exponentially decaying correlation function, like with exponentially with exponentially decaying interactions. So that requires a little bit of thinking. But that's why I like this picture. So basically, if you in practice want to write down your Hamiltonian in terms of an MPO, it's often useful to have this finite in view, and that allows you to engineer the terms, and then you can just convert this to a matrix. Yeah. Yes.
Are not site dependent, right?
That's right. Here at this moment, I'm just assuming that's the same sigma everywhere. But of course, same as for the matrix states, I can also say that, well, I have a M1, M2, and M3. And this, you could say that, well, maybe you have a mixed spin model. You would say that on the even sides, you have a spin 1/2. On the odd sides, you have a spin 1. And then same thing works.
And summing over the D's, what would happen is that as you product it, you'd end up getting nearest neighbor coupling between sigma. Right?
No, but
I'm just trying to see how you generate the Hamiltonian that you started with from this MPO.
how this applies to our
To the initial Hamiltonian.
so you're asking, how do I get from this representation back to our Hamiltonian? Yeah, I mean, all that you have to do is to just multiply the matrices, and then do exactly what I'm showing here. And maybe this is a nice exercise. So you just take this matrix here and use regular matrix multiplication rules to multiply it out and project on these states, and you should get exactly this Hamiltonian back. Right, so you get exactly these terms. You get sigma z, tensor dot sigma z, tensor dot identity plus blah blah blah.
Yeah.
I mean, this follows directly from the matrix multiplication rules.
And what is the limit? Like, what Hamiltonians fall into this category that you could write them as MPO versus not? Are there some Hamiltonians that you can't represent?
Right. So if you, for example, take Hamiltonians that have algebraically decaying, so if you would have some Coulomb interaction or something like this, then you cannot bring it exactly into this form. Then you would need to make some approximations. So and then it's a little bit more complicated, because, for example, what you could say, well, you can now ask what is now the most efficient way to approximate it, and then you maybe can approximate the algebraic decay by a sum of exponential decays and so on. Yeah. If one dimension infinite, you can do whatever you want. Yeah. That's right. that answer we always have, right? So if you just yes. Good. So now I hope that I could convince you that we now have our Hamiltonian, and the Hamiltonian can now be brought into this nice graphical form. And now, well, coming towards our variational method, what we actually now want to do is we want to take our wave function psi of chi, and we want now to calculate the expectation value of our Hamiltonian. If our state is in this canonical form, it's by default normalized to 1. I mean, the way that we defined it, so we don't have to divide by anything here. So now what would this be in terms of our graphical notation? We have our MPS. So these ones here would, for example, just be our matrices B. And now we apply to it our matrices M. This is the MPO, where here we have these matrices multiplied exactly in the same way as I just defined. So this one here would be 1, 0, 0, 0, and this one would be 0, 0, 1. And now we just multiply this thing here. Now that we have B star. Oh, let me just use the canonical form, sorry. So we have here gamma, lambda, gamma, lambda, gamma, lambda, gamma, and then we have here gamma star, lambda, gamma star, lambda, gamma star, lambda, gamma. Right, so this is now how we can calculate the expectation value of the energy. This
Sub chi.
what?
Chi sub chi.
Oh, this should be a thanks.
Chi
A psi chi. Exactly. So what I mean by this is now a matrix product state with a Bond dimension chi. Yeah, thanks. Okay, so everyone happy so far? So we do have our representation of our Hamiltonian in terms of an MPO, and there I at least try to convince you that at least for the Hamiltonians that we're interested in, we can just analytically bring it into this skeleton form, or like this kind of MPO form. And now I can just calculate the expectation value of my MPO with respect to an MPS in this form. And what I want to do now is, now I want to optimize the kind of set of my gamma and lambda to minimize the energy. Minimize the energy. And having this in mind, we can now come up with an algorithm of doing it. And this will be now exactly the DMRG algorithm, because what we can do now is the following. We say that, well, we have our expectation value of the energy, and now we want to change these lambdas and gammas in such a way that we just minimize the energy. And one way of doing it is that we now just, let me just maybe use a sponge. So now I can just remove some. I remove some of those here. So I just remove some of them, and then I just trying to find better matrices here, right? So I keep everything fixed. I keep all the matrices away from this one fixed, and now I'm trying to find a better kind of theta tilde to use the same language that we had before. I'm just trying now to find a better theta tilde in order to minimize this guy. And this is now fairly easy because I can now, if I have my Hamiltonian in this canonical form, so this is now no longer, it used to be the expectation value when I had everything in it, but now if I remove one matrix and I'm keeping my indices alpha, beta, and alpha prime, beta prime, and then I have here I and I prime. Now, this is actually, after removing this matrix and these lambdas, now this is actually what we call an effective Hamiltonian. So we have alpha prime, I prime, beta prime. So this is now the Hamiltonian projected into our effective space, where these are now the Schmidt states on the left, these are the Schmidt states on the right, and this is now the local site. Right? So now we have a representation of our Hamiltonian acting on our vector space, but in projected onto this Hilbert space spanned by the Schmidt states and the local states. And now on this one, I can just use exactly the same technique that we used in the very beginning of the first lecture on Monday. So now we can use iterative methods for finding the ground states, right? So now basically use an iterative eigensolver, for example, the Lanczos algorithm, to find the ground state of H alpha I beta alpha prime I prime beta prime. So this gives me now a new kind of theta tilde, and this I now can put back in, and now I'm going to the next matrix. And then I can just go left, right. I can now go through all of these matrices and keep minimizing the energy by tuning the individual matrices. And the hope is that this will ultimately give me, get me to the global minimum. Right? So basically the idea would then be that we maybe start at the left one, we take out the leftmost one, we minimize the energy, we put it back in, go to the second one, minimize the energy, go back, and then as step as the kind of iteration or sweep, we would then find that the energy is eventually converging. Yes?
The eigenvectors of that Hamiltonian and the theta tilde.
Right. So what we have here is we have now our so now if we just take out just a single matrix, now we have our H alpha I beta comma alpha prime I prime beta prime, and now our we just multiply this with theta tilde times, and then we have here alpha prime I prime beta prime. I'm now summing over identical indices, and this one here would be E naught times theta alpha I beta. Right. So if I'm finding the ground state, then the grounds, like multiplying then the matrix here with the ground state, would be that would be an eigenstate of this effective matrix with the lowest energy. This is what you're asking? Yeah.
So to be sure, how do you guarantee that once you find the ground state of this local effective Hamiltonian,
yes,
and you plug that into the whole wave function, that minimizes the variational energy of the whole Hamiltonian on the big state? And
that is now, thanks for asking, and I was about to disclaim this. There's no proof for this, and in fact, you can find counterexamples where it doesn't work. So the DMRG method, you can actually prove it. There are cases where DMRG will not work. But in practice, it works extremely well, and thousands of papers are written using this algorithm, and it finds good solutions. But there's no proof, and in fact, there are counterexamples for this not to work. Right?
It doesn't work.
You can construct cases where the DMRG algorithm would be stuck on some local minimum, right? So basically, if you just, I don't know, have some abstract way of presenting, here are your parameters, the gamma, like these are now the parameters in your global MPS ansatz, and this you get some energy landscape of this, and this one here, I should say this one is your global minimum. And you can construct cases where you're just running the DMRG algorithm, and it would be just stuck in a local minimum, and it wouldn't find the global minimum. No, not necessarily. Well, this is because the way that you're just doing the optimizations, because each time you are doing, like the way that at each step you're just minimizing the ground state of your effective Hamiltonian, and it's not guaranteed that you just have a pathway to actually to get to the ground state.
Yeah, so even if you start like 1,000 times randomly and prove that you could never reach
if you say that you start from,
Random start.
okay, no, that if you just allow yourself like an infinite number of runs, maybe then it still can prove. I mean, what is actually known is that if you just for a given instance, it might not necessarily converge. Yeah. Well, it's not. There is another algorithm. There is a related algorithm. I forget who came up with it. Maybe someone can help me. Like someone from Caltech, like some computer science person came up with an algorithm that actually provably converges, but in practice it's actually much slower than DMRG. So that's why no one is using it, but people keep using DMRG and rely on that. In most cases, it does work. Yes?
But does minimizing the effective Hamiltonian at least minimize the variational energy among the states that only differ from the original state by that one tensor?
I'm not understanding the question.
I guess my question. Yes. Okay.
Okay, but let's still clarify so maybe other people also didn't understand what you mean.
So let's say I give you some starting state, and all you're allowed to do is change the state by one tensor in one place.
Yes.
Is minimizing the variational energy of H among all those states tantamount to minimizing?
Oh, I see. Yes.
Yeah,
Right.
minimizing H effective.
Right. Yes.
So, just by intuitively looking at it, it seems odd that it would ever be able to escape a local minimum.
Why not?
It feels like if all of my other tensors are somehow near a local minimum, and I try to change one of my local tensors, it will get stuck there. Do you have any intuition why?
No. There's one way to see how it will definitely work would be if you would allow for a bond dimension which is extensive, right? Like let's say that you are playing this game here, but you're having now a bond dimension which is as right. So yesterday when I showed it, I gave this kind of algorithm how you can turn any state into an MPS if you have an exponentially large bond dimension, right? So basically that each of those has a full Schmidt rank. If you are in this case, then the effective Hamiltonian is actually identical to the full Hamiltonian, right? Because then you would say that, well, the Hamiltonian has here, you have a let's say that you just happen to have this just in the middle. Then you would say that, well, here you have a bond dimension of 2 to the L half. Then here you have a dimension of 2, and here you have a dimension of 2 to the L half minus 1. And then you would see that this is actually spanning the full Hilbert space. So then this would be just a funny representation of the full Hamiltonian. And then at each, like the moment that you start, like step 1, you have the right energy, right? So in this case, no matter where you start, you get the right ground state energy right away. The problem is that we don't know this basis right away. So we just start somewhere and we just keep basically doing two things. Like the one thing is that we locally optimizing basically the energy, and also we are optimizing the basis.
When I'm diagonalizing this local Hamiltonian, I'm essentially doing something non-local to my wave function.
Yes, definitely. No, but this is the thing, and this is maybe like the somewhat. And let me just go back to what I was making this point also yesterday. Like when I'm writing my wave function psi in terms of the sum over alpha I j beta, and then I have my theta I j alpha beta I j beta. This is not a local wave function. It's a wave function which is really globally, where you would say that, well, you just have just a representation. We would say that you just have two sides represented locally. So you have the full basis here locally, but everything here and everything here is described in terms of the Schmidt states that you have, right? So basically, if you have a full Schmidt rank, it's actually just a complicated way to write down the wave function. But if you're just truncating it, then it becomes an ineffective model. But it's really, if you're now changing this guy here, the change can be extremely non-local.
Because I'm changing the Schmidt basis.
Well, no. Even if you keep this basis and you just modifying this, it's a global change of the wave function, right? Because these Schmidt states are not really local. They can just extend to your system.
I'm changing the wave feel on all the other sides.
Exactly, yes, exactly. So that is very important that even if you have a matrix product state, you just do a change of your local matrix. It's not a local change of the wave function. Yes?
So, could I have area law and I can keep all the bond dimensions necessary to capture all the entanglement?
Yes.
And then I play the same game.
Yes?
Can we say at that point that we would be more likely to converge to the real ground state? Like, it would go to global minima rather than local.
No, but I think that these kind of counterexample you construct, there is a solution in this space, but there is a solution to your problem in the manifold of MPS.
Yeah.
Because otherwise, of course, if you just say that you have some system where you don't have an area law state, then the solution is simply not in the manifold of MPS. But the concern one has is that the DMRG, even though there is a solution to our problem in this manifold, we might not necessarily find it. Yeah. Yes?
So since if you want to do this, you need some initial guess of gammas and lambdas
For what?
to do this optimization.
To do this optimization? No. I actually am showing how to do this in a moment. So you don't.
Then, okay.
Maybe once I went through the algorithm, you can ask again.
Sure.
Yeah.
Practice, how does the time?
That also depends. So for example, you could have scenarios where the bond dimension is very large, and like the bond dimension of the MPS is very large, and the bond dimension of the MPO might be very small, right? So just maybe take a critical point of the Ising model, then you just get a 3-dimensional MPO, and then constructing this effective MPO might not be too bad. And then you have to do a Landshaw's algorithm, which is a very high dimension. But if you just take another example where you have a state where the MPS is maybe or slightly entangled, so you just get away with a very small bond dimension, but still you might have a very large MPO, and then constructing it might be more expensive. It really is a case by case.
Thanks.
Yeah?
Slot theta tilde back into the empty space.
Yes?
Do you have to bring it back to canonical?
Exactly. This is what I'm showing in a moment. Yeah. Yeah?
I just wanted to ask this. So suppose I did DMRG, right?
Yes.
How do I know that I got the right ground state?
You don't.
Okay.
No, that's a leap of faith, right? Basically, yes. No, but this is indeed one has to be really careful with it. That if you just running in this, or as someone brought up, if you just run the code and you're consistently getting the same state, so it becomes really a bit of something one has to be careful about. Yeah. Yes.
So what you actually wanted to optimize is, isn't it like theta star h theta, and that's, I mean, you want to take like the contraction of h between theta star and theta. So, and theta isn't the unitary. So how do you?
Well, I mean, this is just an eigenvalue problem.
But I mean, what you actually wanted to do was find the theta that would give you like the minimal total value for this contraction of the whole network, right? And
this is what at each step, I'm just saying that, well, I have a Hamiltonian of this form, and I want to find the ground state of this Hamiltonian. For this, I'm just solving an eigenvalue problem, or doing iteratively finding the lowest energy state.
Well, so I think what he's asking is like where is it from? I think that
Where's what coming from?
no, I was thinking of something else, but I'll just.
Okay, good. Let me just maybe some last question on this now, and then I want to actually go to the algorithm quickly, and then maybe because some of the questions might already be answered from actually discussing the algorithm, but
Maybe you can answer this later, but I'm just wondering, like, as a practitioner of DMRG, where's most of your time go when you're doing calculations?
it's really, you mean in terms of the algorithm? As I said, it really depends. I was trying to outlining this problem that you could have cases where maybe D is 500, but chi is just 2. And then this has a very different behavior. And they're even, depending on which is larger, there are also different ways, like the order of contraction can be different for different cases. So
Yeah, but I guess I'm wondering, like, you, for example, does most of your time like go into running the calculation 100 times and to like to convince yourself that you found the global minimum, or?
Also, that depends. I mean, if you just look at critical systems, they are very suspect. So then you just really often run it multiple times because you might be more likely to be trapped in some local minimum. If you have a system with a large gap, then it usually quite convincingly converges to the right result. Yeah. So I don't think I can give a universal answer to this question. Good. So in the spirit as I did yesterday, I also want now, instead of drawing all these diagrams, I want to just now go over like these slides. Maybe it's also a good way to see this in a slightly different view. So this is now again the idea of having an MPO applied to an MPS, and having an expectation value of an MPO with respect to a given MPS. Well, now this was the story that I was telling, the finite state machine as a, and now basically coming to this idea that we just construct the effective Hamiltonian, and then we just now have like the task that we are then facing is that we have to just diagonalize the effective Hamiltonian, then we're just moving to the next side and so on. And the way that we can now do this is very similar, if you just write it this way, to what you learned in the TBD algorithm. So basically what I'm doing is I'm actually not removing just one matrix, which is also working perfectly fine, but this is not what I'm doing here. Is I'm removing two matrices, and then I'm having this wave function theta exactly in the way that I've written it down here, and as I've written it down yesterday, this is just a representation of the full wave function, just using a mixed basis of Schmidt states to the right and left, and local states I and j at the position where we're doing the optimization. So now, and I think this was a question asked Monday or about the Lanczos or these iterative algorithms, if we actually have a good guess of the initial state of, if you have already a good guess of how the ground state looks like, we can usually reduce the number of iterations. But here, now we just take out a bunch of these tensors, and this gives us already the wave function that we have at a given moment. And then we are using this as an initial state for an iterative eigensolver to then find the best approximation of the ground state, finding the ground state of this effective Hamiltonian. Right? So, and this state, and this was a question just asked, now we just get our theta tilde. This is now our ground state of the effective Hamiltonian. And then we just play exactly the same game that we did for the TBD algorithm. We perform a singular value decomposition to basically reduce the bond dimension here again, right? So just reduce the dimension here from d times chi to chi, to just rotate it into the effective basis. And then we just multiply it with the inverses of left of right, because we these guys haven't changed because we didn't touch the other bond. And now we get updated tensors at a given position, and then we can now move to the next, and move to the next, and we can just now sequentially go left and right through our system until our the state has converged. And there's like another thing that I can do in between, because usually, well, the way that I presented it here, at each time when I'm somewhere in my position, I would just have to multiply everything. But if I'm just doing it sequentially, I can just doing these multiplications step by step. So basically that when I'm optimizing it, I'm just updating my left part and my right part so that I don't have to do it over and over again. This is just a step that just helps me to save a number of contractions. So I just, as I go along, I'm just building up the left part and the right part so that I don't have to do this at each shot, right? So basically I just have this one, and then I'm just moving on. Each step takes O. That's right, yes. And the scaling, right? So things about the scaling. So basically, all these steps scale with a bond dimension to the power 3, right? So for example, the singular value decomposition scales with the third power of the dimension of the matrix, and the dimension of the matrix is chi times d. So it scales then with d times chi to the power of 3. So, and now let me quickly go over how it actually looks like in Python code. And this is what you find on the Google Drive folder. A lot of things will look very familiar to you because this is exactly what we had in the TBD code. So we have to construct our initial state where we just now choose just a ferromagnetic MPS, which is just a product state, which is very easy to produce. And now we construct the MPO. This is exactly the matrix product operator that you've seen on the left side of the board. Then I have now my function calculating an expectation value of an MPO. This is now calculating exactly this object. So we have psi, h, psi. And then there's the function correlation function. It's exactly the correlation function thing that that we looked at on yesterday. And now I have here, and this is in the case of defined in terms of a Python class, we have the effective Hamiltonian. So the effective Hamiltonian has now the left part, the right part, and the MPO. So this is now constructing exactly this object where I just removed two of these tensors. So this is now the Hamiltonian in the effective basis. So this is now my Hamiltonian alpha I j beta alpha prime I prime j prime beta prime. So this is in these lines of Python. And now I just use functions of Python to diagonalize it. So or basically to like use the lunch shot. This is exactly the same function that we called on Monday to do exact diagonalization. And now there's this update function, which is multiplying, like iteratively building up the left and the right part, and is getting back the tensors. This is exactly the same stuff that we did yesterday in the TBD algorithm. And now we're just doing this from left to right. And that's it. So now if I run it, I hope it does. So now it just takes a few seconds, and we see here that for 16 sites we get, after just a few sweeps, we just get the result up to machine precision compared to exact diagonalization. And now we can also just go back to our phase diagram. And now we can here, within a few seconds, get then the phase diagram up to, it was actually, let me just run it real quick, just to see that the speed gain that we get compared to, or what do I not? There's something. This is a problem with if I just do something actually in real time. So you see that didn't take long, right? So now this was like 0.1 seconds to get then this for L equals to 16 up to machine precision. And now we can also just do it for the full phase diagram. And now we can, you see it's significantly faster than yesterday. And now we can also go to 64, and this takes about 10 seconds. And we just now get a much better picture of our phase diagram, where we see that the magnetization here drops to 0 around a field being of the order of 1. Yes?
Sorry, are you finished with that?
I'm finished.
Okay.
but
So why do we sweep? So if I found the theta tilde that minimizes energy among the things that change locally, why not replace all the tensors with theta tilde? And, so taking advantage of translation variance somehow.
Right. So here there's a few things. So first of all, what we are doing here is we are doing with open boundary. It's the tensors are not exactly the same. So but then there's also another thing that we have to be careful about, and this is maybe worthwhile pointing out. Let's say that we have a matrix product state, and now, well, let me say we have tensors A, B, C, D, E, And now you say that, well, you're doing some optimization here for your tensor. And then you say that, well, now you just replace all the other ones by the C because you found it to work quite well. But the problem is that there's this gauge degree of freedom. So basically, this X, and you can choose like all of those. So basically, if you now just take this matrix, which was really good for having these as the neighbors, and you just now replicate it, it's actually you don't take care of the gauge to the left and to the right. So it might be a horrible thing if you just replace all the others by this one. Right, but the that you've chosen, right, so again, they are not all the same. So this is the X between B and C, and this is the X between C and D, right? So all of these X's are chosen differently. And if you just basically do the optimization, it's done with this gauge here. So if you want to just replace it everywhere else, you have to fix the gauge. And what you can do, but this is something that I chose not to discuss here, you can actually also right away make the ansatz, yet you have the same matrix everywhere, and the system is actually infinitely large. And then indeed, this can be done, and it is done. But this is a different question. Like, this is basically, you're assuming a sort of a uniform MPS. That's your ansatz, where basically your ansatz right away is this, and then you can also solve it directly in the thermodynamic limit. But this is what I'm chose not to talk about, not to confuse you more. There are both options possible. You can do it iteratively, or you can do it self-consistently. It's like either called IDMRG or infinite DMRG. Then you just basically iteratively build it up. And there's also a way that you just do it basically self-consistently, and this is called a variational uniform MPS.
That method.
That's right. But there are different techniques or different ansatz. But the scaling and how well they work is rather comparable. Yeah. Yes.
The uniform MPS with, imagine that infinitely far. I mean, is that immoral somehow? What's like?
No, there's not immoral. This is done. I mean, like, you can basically do this if you have a problem where you just maybe want to do it right in the thermodynamic limit. That's fine. But in many cases, it's a good idea. But if you say that you have a critical system, you want to do scaling. It's I mean, this is a perfectly fine technique, all good, but I just chose not to talk about it, not to confuse people more, because there's like many different methods, and there's just a limited time. That's why I chose.
Is it not variational for anything?
No, but as I said, like none of these methods, like these methods, well, they are variational. It's just that you're not guaranteed that they are going to find the ground state.
But the infinite one, I guess I have an infinite Hamiltonian.
Yes.
So
but
is there some
the energy density is still variational.
And this would be variational for the energy.
Yes. Yes.
Does UMPS capture translational symmetry breaking that happens?
Well, yeah, it does. Leads to instability, because let's say that you have a state which is, let's say that your ground state is of this form, but you're choosing an ansatz which is translation invariant. Well, if your system spontaneously breaks the symmetry, well, if this is a ground state, this is also a ground state. So basically, what would then happen is that the solution, if you're searching in the space of uniform states, it would actually not find a symmetry broken state, but it would give you a cat state, basically. But that would also lead to certain instabilities in the algorithm. Yes? Right, this sweeping has the advantage that you can basically from the kind of left to the right canonical form. If you just, there are technical advantages of this. We can talk about it in private later, but there are good reasons to do this with a sweeping left and right, because otherwise it becomes less stable. Yes?
I mean, it still seems to me that you need to start with an initial guess, right, of your matrix product state.
Yes.
guess some initial gammas and alphas.
Oh, yeah, this way. Right. So the algorithm, you start from some initial state, but the generically that doesn't really matter. It's the same as you just, for example, do a Lanczos algorithm. You have to start from some initial state. Like for any iterative method, you have to start from some state. But if things go well, it really doesn't matter how you start. Like you start somewhere in your Hilbert space.
Okay, but are you saying that if you start at some states, you'll get stuck in a local minimum, but with the same algorithm and Pollmann and everything, you start from a different state, you can get to the global minimum?
Right. Okay. So if you take a benign case where DMRG is working and it's all good, it really shouldn't matter what your initial state is. You're just going to find the same solution each time, right? So I don't know if you if you just take this problem here and instead of having a ferromagnet, you just start maybe from an antiferromagnet or from a random state. You just really find exactly the same solution. And I invite you to play around with this code to see if you can break it by choosing a stupid initial state. But if you have very kind of cases like we're just really scaling up things and then indeed it can depend on the initial state and you have to be a bit careful about how to craft them, right? So for example, if you have systems that spontaneously break the symmetry, often it might be good to actually initiate it with a symmetry broken state to avoid this DMRG finding these cat states. So if you are a practitioner, that will in the end go quite some time into actually engineering good initial states, or also like the way how to start this algorithm that you maybe ramp up the bond dimension. So there are all sorts of tweaks and things that you do, but there's no time to go into all these details. Yes? Yeah, but this is the reason why in this algorithm I like to choose. I choose here to start with a bond with this two-side update, because the two-side update, as we did also in TBD, immediately allows to grow the bond dimension, right? As we discussed yesterday in the TBD, because what we do here is we just start from a bond dimension chi dd, and then after this we have a bond dimension d times chi here, and then we do the SVD, and then as needed we can just reduce the bond dimension down to chi. But in the beginning we just let the bond dimension just grow up to wherever we want to go. If you just do this one-side update, it's also perfectly fine, but then you need to have some extra step to actually consciously grow the bond dimension. That's why this is very easy to use. Good. Yeah, so I mean, I think time is basically up, and there's also time for me tomorrow that because what I want to show you tomorrow is now just on the slides. I want to show you some applications of DMRG, because looking at the Ising model, I think it's really good as a benchmarking testing case. But now I want to show that also we can just use the same algorithm on problems which are maybe more of interest to you at this moment than the Ising model, which is already solved. And I want to just show you some of the examples, and also how to use these methods to look at dynamic response functions. But then I just do this probably tomorrow. Yeah.
Take advantage of symmetries.
And this is a very good question. This is also indeed important. So symmetries are really like, if you want to look at more complicated problems, it will be very good to get most out of it, and then we want to use symmetry. So one way of, if you have a translation invariant system and you want to do it, then you can do it in the thermodynamic limit, and that saves you time because you can optimize the same matrix over and over again. But then there's another way how symmetries can help a lot. Let's say that we have a system with a U1 symmetry, right? Let's say we have a system where SZ is conserved. And now if we take a state then, and we just do a Schmidt decomposition, for example, of our state, psi is equal to the sum of lambda, alpha, alpha left, alpha right. Now if say the total state has SZ equals to 0, then we just know that each of those alpha also has a quantum number. So we can assign some SZ quantum number to every Schmidt state, and this one here is going to have minus SZ because both of them together will be SZ equals to 0. So this means that we have these quantum numbers. But if we now take this representation of our state, for example, our theta that we have which is now like I, J, alpha, beta, then we just see that this is 0 whenever SZ alpha plus SZI plus SZJ plus SZ beta is not equals to 0, right? So we see that, and this is like non-zero if this is actually 0. So we see that that we see that many of the elements of our tensors actually have to be 0. So then we can now, instead of operating on all subspaces, we can now just reduce it to some sort of block diagonal structure where the symmetries are actually fulfilled, and that makes things much faster, right? And including this into the code is doable, but a bit cumbersome. But the good thing is that if you're just using these packages such as iTensor or Tensor Network Python is 10Pi, they have all this built in. If you have a Hamiltonian that has, for example, a U1 symmetry, and you just choose an initial state that has a U1 symmetry, then it will automatically perform all operations using these symmetries.
So you want to get the first excited state of the transistor lysing model, you can just tell it to look at the odd magnetization sector.
That's right. If you just have a case where the ground state and the first excited state are distinct by a certain quantum number, you can just choose an initial state with a given quantum number. Or maybe if you say that you have a total SZ conservation, you can find then a ground state in each SZ sector and then compare the energies, for example. Yeah.
I have a question that also the DMPF, UMPF, like, so does the bound dimension grows with like the cell size?
No. The bond dimension, it doesn't, I mean, if you have like a problem and you just group them in certain ways, so let's say that you have A and B, in general, it doesn't matter. Like the bond dimension, unless you have a case which spontaneously breaks the symmetry, then it does matter, because if you have like this A-B pattern, for example, it would allow you to spontaneously break the translation symmetry, while the perfectly uniform ansatz would not. But other than that, it.
So my question is that so if I want to capture this spontaneously broken symmetry.
Yeah, then it matters a lot, because then basically there's a factor of 2 in the bond dimension, right? So here you would basically, if you just visualize this state here, you would just have one block which corresponds maybe to this one, and you have another block corresponding to this one. That means that each one has a bond dimension chi. So basically in this case, if you want the same accuracy to get the state, then you would have to double the bond dimension. Yes?
Theta is a local thing, but
It's not. Theta is not local. It's a. I mean, this is the point I'm trying to like if you just go back to the very beginning when I was saying that, well, we can now exactly do this transformation if we just keep the full Schmidt rank, right? So then basically, and I have written it down here, right? So if I have this representation in terms of this theta, it's just that I'm choosing to describe everything on the left with Schmidt states, which are a complete basis for this guy. If here and here and it only becomes local-ish if we just have a system with algebraic, with exponentially decaying correlation functions, because then these Schmidt states would basically only describe exponentially, but it's not local, because the Schmidt states have a support on the entire left half or the right half.